Okay, so let us start. Good evening, everyone. Welcome back to today's Asset Colloquium. For those of you who are not from TIFR family, just a word or two on what Asset Colloquium is. Asset Colloquium is a forum. Of course, it stands for Advances in Science, Engineering, and Technology. This is a weekly colloquium forum which mainly specializes on talks and colloquia based on instrumentation, electronics, detectors, software, and topics like that. So this, of course, complements to two other colloquia that the TIFR organizes every week, one on Wednesday, which deals with natural sciences faculty topics, and one on Thursday, which is mainly on mathematical sciences. Of course, the asset is about 30, more than 37 years old body. And as I said, it organizes talks mainly specializing in technology and engineering areas. Today, I'm very happy to host one of my old friends, Sureshkumar. He's going to talk today on antennas, RF electronics, and signal transport system in building the upgraded GMRT. I'm sure many of you have attended and remember an excellent talk by Professor Yashwant Gupta last week on the overview of the radio astronomy in India, which spanned all the way from Kalyan Radio Telescope to upgraded GMRT. Sri Sureshkumar is the group head of the RF and fiber optic system at GMRT, and he has been, as I said, working since 1992. Is a veteran in that sense on this field at NCRA-TIFR Pune. He obtained his BSc in physics at Madras University and a BTech in electronics from Madras Institute of Technology, that is MIT in Chennai. Later, while working at NCRA in 1998, he completed his master's in engineering at the College of Engineering, Pune. He specializes in, of course, RF or fiber optic systems, and that's what he's going to talk today, and has designed the signal transport system of the upgraded GMRT. That is the main focus of today's talk. His other areas specializations are antennas, the RF receivers, gigabit Ethernet networking over fiber, and RFI, basically radio frequency interference mitigation. So with these few words, I welcome Sureshkumar and request him to deliver his colloquium.
Thank you, sir. Thank you for the introducing me here and for the opportunity. I think my voice is clear. Yeah, today with the introduction given by Professor Yashwant Gupta last week about the GMRT, you would have heard about the upgrade has happened, GMRT upgrade after performing a decade and above. And today I'm going to talk about how the upgrade has happened in the antenna systems, electronics, the signal transport system, what made the change and how the telescope was brought to this international recognition after the upgrade much is what I have to put it here. And plus the challenges we have undergone in building the upgraded system is what I'm going to highlight. What are the specifications has been considered here and how it has been achieved. So those details will be shared in this talk. Yeah. My slide, what happened? Yeah. So my talk will be of 15 minutes on antennas, RF electronics 15 minutes, signal transport system, which is the fiber optic system, 15 minutes. And the future scope, what we have for the upgraded GMRT on the engineering side will be on another 10 minutes. So let me start with some introduction to astronomy because to have a flow, I have to start with this. The radio astronomy is a little different from the regular astronomy, optical astronomy. And you know that the astronomy has multiple windows through which you see the sky. You can see in infrared, optical, ultraviolet, X-ray, gamma ray, and the radio waves window is one of the things, which is a wider window where you can see from few tens of megahertz to 1 terahertz kind of bandwidth. You can see the sky without any absorption in the medium. So radio astronomy works on this window. Then little history. Carl Jansky is the father of radio astronomy. He was surprised to see some signals coming from the space, and they were the radio signals which are coming from the space. And he is the first discoverer of radio signal from space, and is the father of radio astronomy in 1936. Then we have Grote Reber. He is an engineer from Marconi, and he has built in his free time a telescope in his backyard, and through that he made some discoveries using radio sources. And GMRT was recognized by this Grote Reber's foundation also. When you visit GMRT, you can find his ashes kept near the control room as a recognition to GMRT. This has been done. And as a telescope, what happens is the signals coming from space, they come as parallel rays, and you have a parabolic reflector. The signals get reflected from the parabolic dish and gets pointed to the antenna feed, which is placed at the prime focus of the dish. And there the signal is taken by the amplifier, signal conditioned using some filters and further amplification, and then it is brought down and sent to the control building for further digital signal processing. So this is the basic block diagram of a radio telescope. And the signals, what we are looking at is that it is, astronomers call it as like Jansky is a unit, which is 10 to the power of minus 26. Let me put the pointer, which will be useful. Yeah. So one Jansky is like 10 to the power of minus 26 watts per meter square per hertz. Suppose you wanted to acquire 1 millijoule of energy, okay, for the continuous observation, people say that it takes 1,000 years to acquire 1 millijoule of energy from space. Yeah. Yes. Hello.
Your voice is not clear.
Voice is not clear.
Voice is not clear.
Is it okay now?
No. Yeah. Can you continue?
Yeah. Okay. So my voice is it clear now? No.
No, it's breaking off a lot. Okay. I hope.
No, actually it's fine. Actually, it's problem with your end. His speaker is fine, I think.
Really? Oh, just check it out, because sometimes net speed matters actually.
It's fine from this side also.
Yeah, to begin with, it was nice.
Yeah.
And it actually matters.
I don't know.
You changing your laser pointer.
Okay. Okay.
No, I think speaker is fine.
Okay, thank you. Then I will introduce to another parameter, which is called as angular resolution. You know that to resolve any object in the sky, you should have a like fine beam to pinpoint that this is star 1 and star 2 like that. It is like that simple. The human eye has an angular resolution of 17 arc seconds, whereas a 100-meter radio telescope could get only 440 arc seconds. Imagine a 100-meter telescope could not compete with the human eye. So then how do we do with the radio telescope? So then comes the radio interferometry. What people started doing is they started building 2 telescopes and spaced at a distance of say 30-kilometer distance. And the equation goes like this: 1.22 lambda by baseline distance. Baseline is the distance between the 2 radio telescopes. And this becomes like 1 arc second is angular resolution. So that is a big jump for the radio astronomers to start with the interferometry. So things doesn't stop there. People started moving to aperture synthesis. Aperture synthesis is Sir Martin Ryle. He got his Nobel Prize for this. And in 1950s and 60s, he showed that you can synthesize a large aperture, okay, with multiple small telescopes located and spread over the earth, right? Okay. So he could synthesize the beam, a very fine beam, and with a very good angular resolution, okay, which is equivalent to a large simulated aperture with small antennas spread over large baselines. Okay, so this was the another boom that people started building large small antennas to synthesize a large aperture, and from that You synthesize a narrow beam for the radio astronomy purpose. Then coming to the array, okay. So the aperture synthesis involves like multiple antennas. So multiple antennas, how do we arrange? That is another challenge. So there are two major things like an Y array, like GMRT and VLA. You can see in the Google map, we have plotted this. There is a shape of Y approximately. And things like SKA, square kilometer array, and LOFAR, they try to follow the spiral galaxy. Okay, what it is said is that like when the antennas are like 20 to 40 antennas, the Y array should be okay, and whereas more number of antennas are there, it's better that we go with a spiral array configuration. So what it matters, the thing is that when you have a telescope and you are pointing to the sky and you try to make a perpendicular plane to the direction of your viewing the sky, okay, and that plane you call it as an UV plane or the coverage plane, okay. So in that plane we actually try to get the Fourier transform of the sky brightness seen by every baseline in the sense like antenna 1 and antenna 2, antenna 1 and antenna 3, like that you form multiple beams, and with earth rotation continuously these baselines keep changing and you get a Fourier component of the brightness, you get it, and that distribution covers that the larger aperture synthesis area. So the UV area, suppose the baseline is a 30 kilometer, the UV coverage plane we also consider as 30 kilometer, and how much is covered your data on that, okay, that is the coverage. So that coverage is good enough for Y array as well as the spiral galaxies, spiral antenna arrays. Okay, so the array depends mainly on the number of antennas and how good you cover the UV plane and synthesize a very good beam, okay, with the earth movement continuously. You should ensure that as the earth moves, every baseline is pointed to the source. Okay, it should not be like a situation where some of the baselines are not visible or something like that. Okay, so that is what they call it as UV coverage, and based on this array, Y array and spiral arrays are configured. So there is a small table I have given. The angular resolution goes like for a single dish, it is lambda by 4. Lambda is the wavelength and d is the diameter of the single dish. And for a n number of telescope array, like 30 antennas in a GMRT, the largest baseline defines the D here, and naturally the resolution will be good. And same with the collecting area also, it is like n times d square when it is an array antenna. Now coming to, with this introduction, let me come to GMRT. GMRT telescope, the array you can see here, it's a Y array of 14 kilometer distance, the radial distance, and the far away baseline you can get is about 28 to 30 kilometer distance. You get it, the largest baseline. As well as there is a compact array where you can have closely spaced antennas and short baselines, which is used for certain astronomy applications like yeah, we can say a compact source and what you call broader source kind of studies. People try to use these different configurations. So GMRT antenna is 45 meter in diameter, is the diameter of the dish, and it is built with wire mesh to ensure it is light in weight, low cost, as well as wind loading is less, and you don't put much of the stress on the servo systems. And 1/3 of the central portion is made of 10 by 10 square wires, mesh, what do you call it, square mesh, and then 15 by 15, and then 20 by 20. So this is the way the sizes of the wires also is arranged. And the antenna feeds and front-end electronics, what I'm going to talk, is sits right here at the prime focus. The signals fall on the dish, get reflected and reaches the antenna feed. The antenna feed receives it, amplifies it, get the signal down and give to the fiber optic system, and it goes to the control central signal processing station located in the center of the array. So this is the overall working of the telescope. And I have to tell you that why parabolic dish? Parabolic dish has its own advantages, like it has high gain. You can achieve like 30 to 40 dB with a larger diameters, the high directivity, and you can get a narrow beam width. And other thing is that all rays falling on it from sky, it will come all in phase at the prime focus. Okay, so that is the beauty of the parabolic thing. And other thing is that you have to ensure that the beam, the feed, what it is looking to the dish. Okay, here I'm talking like a transmitter, like the antenna is shining the beam to the reflector. It should see to that not much, it should look to the ground. Okay, so only limited illumination you do to the reflector. You don't illuminate the entire dish. If you illuminate the entire dish, there is a chance of like you see the ground, you see some other source outside the dish, and they all will add the system temperature and sensitivity will drop down. Okay, so there is a limitation that you under illuminate the dish so that you don't see unwanted stuff in the dish. So how do you do that? There is a parameter called tapering. You make a tapering value of like this, a maximum 0. You get down by minus 12 dB down, and that point should be the edge where it is meeting. So the point at which it cuts off at the edge of the rim is like minus 12 dBm instead of 0 dBm in the center. So that is how the tapering is ensured. There is another parameter called F by D. This is also important because the efficiency of the antenna depends on that. So we have a spillover. Spillover is like how much the signal falls on the ground. Okay, that is called spillover. And then how much the feed and the feed supporting structure, like this is a supporting structure and the feed systems, how much they block the signal, incoming signal. So there is a feed blockage. And then the illumination, like we under illuminate the dish. So all that matters, and it is optimized that for a value between 0.4 to 0.5, the efficiency is good enough. So GMRT uses an F by D ratio of 0.412. And other efficiency factors of the GMRT dish, it is not only the dish, it depends on the feed and the feed pattern sitting at the prime focus. Like as I told you, the spillover, how much signal falling out, the taper efficiency, where you cut down here, and the surface error, how good is the parabolic structure, that it matters. Then the aperture blockage, how much the feed and the structure block your illumination of the dish, that also matters. Then the polarization efficiency, like you have an incoming polarization and your feed is of a different polarization, then you lose the efficiency there. And other point is that non-single point, you know that parabolic reflector focused signal will come to a single point, whereas any antenna feed you put on top, they are not single feed point feeds, they are larger in size. Okay, so because of this you will lose a little bit of efficiency there. And there are other diffraction and phase errors and mesh leakage, all efficiency matters with these errors. Now coming to the actual feeds, if you come to GMRT, you can see this big dish. Our people will be going up the crane all the way to the prime focus to a height of 25 meters. And it looks on top like this. It will be a very good view from top. Okay. And you can see these are the antennas put there on top. And these boxes, what you see there, they are the RF electronics. So in radio astronomy, the signal which are coming in itself is a very weak signal. So you should ensure that you then and there amplify it, signal condition it, and then bring all the way down through this cable, and then you send it to the for further signal processing. So you should have the RF electronics also put here. And the feed which is focused to the dish, that particular band of electronics will be turned on, and the system works to that frequency band. That is a concept. And we have 4 faces on the turret. Okay, you can keep 4 different feeds. Okay, and that is what we are going to see here. Okay, so what type of antenna feed sitting at the top? So the thing is that since it is a low frequency, the upgrade started focusing on dipole antennas. Like these are the dipoles. You know, it's a dipole is a very common thing, and they resonate at lambda by 2 lengths. Like lambda is wavelength, as I told you. Okay, but the bandwidth of it matters when you try to make the wires or the dipole arms little thicker. Still, we are not satisfied with the bandwidth requirement. So we started putting sleeves above it, top and bottom, and try to get the wider bandwidth. You can say that octave band, okay, kind of bandwidth to these feeds. Okay, so we could get the bandwidth. Then what happens is a dipole will have a figure of 8 kind of radiation pattern. Okay, so the forward beam actually gets focused to the dish, whereas the backward beam, okay, it focused to the sky. It could see a strong astronomical source or something else, so you have to block it. So what we do is we put a reflector behind each dipole and try to boost the forward radiation, okay, and suppressing the backward radiation from the dipole. So that is what we call it as engineering side, like front to back ratio of an antenna. And we use this kind of reflector. Now, other thing is we wanted polarizations. Okay, it is not that one polarization we give, like TV antenna, you have like one polarization. You keep the antenna horizontal, it receives only horizontal polarization. But in here, we need to obtain vertical polarization and horizontal polarization. For that, we started using a cross dipole configurations. Okay, one receives the vertical component, other receives the horizontal component. Now that is done. After that, we found these dipoles are balanced lines, whereas the coaxial cable is an unbalanced line. You know that. So we have to have a balance. So we integrated the balance into the dipole, okay, using a lambda by 4 shorting plate here, and we integrated a 1:1 balance to this dipole, and this becomes matched to the coaxial cable very well. So this is how stage by stage we started moving on the dipole design. The other thing is that you can see all this reflector behind the dipole is conical, not a flat one. Okay, the reason in this is that, as I told you, the taper should be like around minus 12 dB at the dish edges. To get a taper at minus 12 dB, okay, we started building the dipole with a reflector, and we could do it at the center frequency. But since the old feed was like a narrow band, whereas the new feed, you can see it's so wide. Okay, we should ensure that the taper is obtained in all frequency within the bandwidth. Okay, to do that, a flat reflector will not help. So what we have done is we have used a conical reflector of a suitable angle. Okay, and with that we are able to get a nearly 12 dB taper value. So because of this, the conical reflector is used in the dipole antenna. Now, it doesn't stop there. When you put the antenna at the prime focus, the important thing is that at what height you mount this antenna feed above the reflector. As I told you that the astronomy signals or the parallel rays coming to the reflector getting focused to a point. Okay, and it is necessary that the virtual point where you can't see it, you have to place the feed phase center also exactly at that point. Okay, so how do we do it is, we have an adjustable stool, mount the feed, increase and decrease the feed vertical movement towards this dish center and away from the dish center. You can see that the stool height is adjusted like 1040 mm to 1550, 540 mm like that in steps of 100 mm. And then we try to fine tune every 10 mm variation and get the best deflection from the astronomical source for the given feed and the given dish antenna. So the phase center adjustment is one another thing which needs a lot of exercise, and we do that for every feed, and we obtain the best sensitivity for a given feed. Then there is one another problem is that when you have a E plane and H plane radiation pattern, okay, in an antenna you will have a figure of 8, I told you that, but this is a circular, right? So what happens is the beam should be that when you take a E plane and H plane, the beam should be of same. When you overlap them, they should overlap each other. then only you get a circular polarization when you try to combine them. Otherwise, you can't obtain a circular polarized performance from the antenna. But do that. So there is another concept called beam forming ring. We started putting a beam forming ring around the dipole like this, okay, and that has helped. But since the feed is broadband, you have to have two beam forming rings, and that two beam forming ring, one for the higher frequency and for the lower frequency, and you can compress the H plane pattern to match the E plane pattern. This is what done in this beam forming ring in this dipole. Now, with that, I summarize this feed antenna part. This is the old feed. You have a thick dipole antenna, cross dipole. This is a coaxial field and a horn antenna. We are upgraded with this beam formed ring for the 120 to 260 megahertz. And then we have this conical cross dipole for 250 to 500 and 550 to 900 for this one. And L band we have retained, and we are still in the process of working on the similar dipole to replace this. We have achieved it, but we are evaluating it. You can see the bandwidth here and the bandwidth there. So this is what the upgrade starts from. Okay, the upgrade starts from the feed and then it moves down to the receiver system. Now coming to the RF electronics. The electronics, as I told you, the antenna provides like a V channel and a H channel, vertical polarization and horizontal polarization. If I wanted to convert it into a circular polarized signal, I should have a polarizer. So that polarizer is the first component, and then the signal goes to the low noise amplifier where it is amplified and it is taken to a sequence of filter. Either you take the entire band or you can have chunks of the broadband, and then you amplify it and take to the gain block amplifier and then get down to the fiber optic system and reach a control room. There is one another thing, a noise cal is provided just before the LNA here. So this noise source is used to identify whether your system is performing linear or not. Because you are seeing some strong source, you are not sure whether your receiver is saturating or it is working perfect. So you can pump noise, calibrated noise sources along with the signal and try to see whether your receiver shows a deflection with the noise source. That tells whether your receiver is saturated or not saturated. Also, it tells the strength of the incoming signal and whether you are properly calibrated the settings for the front-end systems. That is one thing which is done with this noise cal. And other thing is there is a common gain block. Since each bandwidth feed has individual front-end box with LNA, polarizer, everything. And for one channel and the other channel, you have band selectors here. So these band selectors select the particular band that the feed is focused and bring down the signal. Other systems are on, but they are terminated. Sorry. And this is a solar attenuator. Suppose you accidentally were to see a sun in case, okay, for safety, you can put the solar attenuator, say 14 dB and 30 dB based on the requirement, and you can protect your system down the chain without getting burned. Okay. So this is the various things which I have done for it. Let me summarize as we go. This is the polarizer, what I was telling. I have made a pencil sketch. This is done long, but still I am continuing with that. So you have a V input channel. You divide them and you give a 90-degree phase shift and combine with the other one, and you get a right circular polarized in channel 2, and this you get a left circular polarized signal. So this is how the polarizer works for the GMRT antenna. And then the noise cal, as I told you, this is the noise off and noise on condition. You can see a deflection. If the system is saturated, this deflection will not be seen. Okay. Now coming to the LNA, what happens is the first amplifier is very important, and its noise figure is NF1, the first stage. Okay. And the second stage, what happens is it is divided by the gain of the first stage amplifier. And the third stage is divided by the gain of the first and second stage. So the gain of the first stage should be high, as well as the noise figure of the first stage should be low enough to have a low noise figure, which means that noise temperature is low and the telescope is very sensitive enough. So the LNA design is a very important thing to have a low noise figure. The other thing is that it has two constraints. One constraint is that the LNA is, we don't have the luxury of cooling it. You know that all international telescopes have cryo-cooled systems to cool the LNA, and they reduce the temperature and they happily get a better sensitivity. But in GMRT, we don't have that luxury. What we do is we try to build the our amplifiers, we call it as a room temperature LNAs, okay, which could get close to the required low noise performance for the radio telescope. And this is a really novel. I can show you some of the LNAs which have gone down very much. Like this is a low frequency gone to 40 Kelvin and with a gain of 35 dB. And you can see here from 0 degree to 60 degrees Celsius, the variation in noise temperature is only 10 Kelvin. Okay. The second point is that with the outdoor, these LN is sitting, they should not get varying with environment. Okay. We have to ensure that environmentally it is stable. So the variation is not much from 0 to 60 degrees. And even the gain variation is only like 0.2 dB over this 0 to 60 degree temperature. Now going to the other LNA, you can see this is a band 3, 250 to 500, or you can say 200 to 500 band. The noise temperature at room temperature is 35 Kelvin. Okay, sometimes we get even 32 Kelvin and lesser that. So these are all is a what you call feathers on GMRT designs. In-house it is built, and the important thing is that the OIP3, that is a compression, what you call output intermodulation port IP3 point is like quite high, because it has to sustain the high interference seen at the lower band. You can see here this is plus 20 dBm in the other band. Okay, so you should ensure that the receivers don't go into non-linearity and start giving unwanted products generated by this system. Sorry. So band 4, it is like 550 to 900. You can see the temperature has gone down to like 30 to 35 Kelvin. Sometimes it has gone even to 27 to 28 kind of thing also. And this again, you can see here with the temperature, the variation is only 10 Kelvin and the gain variation is like less than 0.4 with 0 degree to 60 degree temperature variation. So outdoor, it works very perfect here. Okay, there's another problem. What we have gained by reducing the LNA noise performance, we lost in the connecting cable between the antenna feed and the amplifier. Okay, what we thought is we started a novel thing in this upgrade. We started getting the LNA, the polarizer and the noise injection facility very close to the dipole itself. So we split the front end box and we brought the critical LNA very close to the antenna feed and we mounted behind the dipole. So this bringing it closer has reduced the cable length and the loss has come down and the system has improved. And what we have gained by reducing the LNA noise is not lost in the cable loss. So this technique has been implemented in the upgrade and it is very useful. We are trying to do it for L band also. Band 5, this is the existing one, but we have made a high gain 3-stage LNA, which is of 45 dB gain and 32 Kelvin. And this is again the variation with the temperature 0 to 60 degree. You can see like noise temperature varying only 10 Kelvin, not more than that. And this is only like 0.4 is a gain variation. Because for astronomers, it is very important that the gain variation should not be there, as well as the variation in noise temperature also should not be there, because even the phase variation is also very critical for them. The other challenge what we found is that when you are trying to build even a filter at low frequencies, the size of the filters are quite becoming larger and larger. So we started adopting metamaterial based designs, okay, which has helped in reducing the size of these filters. You can see these are sub-band filters for different bands, and you can see this 250 to 500 has made into like a 100 megahertz kind of bandwidth. So by building this subband filters using mathematical technique, and the size of the filter has been reduced with this method. Then we started using integrating subband filters, this type of thing for higher band. We cascaded all this for, not cascaded, we have integrated in one single box. And you can see that 550 to 900, you have subband filters, like every 100 megahertz, you can take the bandwidth and start doing it, or your full entire bandwidth of 550 to 900 could be used in this using this filter. Okay, now what happens is we have wide open our eyes to see all signals from space with wide bandwidth, but we have uninvited gust, which is the radio frequency interference, and we have to block it because they started saturating our system. They started giving unwanted products in our systems. So that has become a great challenge. So our RFA group has started working on to build various filters. I give one example here. So this is a TV band like 175 megahertz and 181 megahertz. This is like a 120 to 260 band. This is a single band. But what we have done is we have suppressed the TV band in this location with this notch filter design of like giving like high rejection. You can see the rejection level, and we could attenuate it. Even then you see small spike coming from the TV line. So sustaining with these kind of interferences at low frequency is a real challenge. And we have started building filters, notch filters to reject for FM radio, wireless services, TV lines at 550 to 500 band, and then 180 band, then satellite interferences coming in, and then GSM mobile, like geo kind of signal, then 1800 megahertz, even though it is outside our band, but they started producing products inside our band. So all these filters have been made by our engineers, and we are ready with it. And every front end, wherever it is required, we have inserted these filters and protected the system from this strong interfering signal. Then there is a common gain block. So this is another problem. So this a single amplifier supports all bandwidth, and it is very wide, like 50 megahertz to 1450 megahertz. But this, since it sees the entire band, okay, it needs a high dynamic range. Otherwise, this amplifier will limit the dynamic range of the system and starts producing products. So this is a new design in the upgrade. We have designed in such a way that it has a very high YIP3 and the system works very good enough. And then we have added RF monitoring facilities with a high linearity and dynamic range. So we have put wherever needed, we have put the RF monitoring so that remotely we can monitor the front-end system sitting at the prime focus feeds. Okay, the overall summary of the front-end electronics, you can see that the system temperature we have reduced for 150 megahertz, the astronomy band, 235 we have reduced, 327 little bit, 610 we have reduced where it really interests people, and L band we have not made a change. In addition to the wideband, we have done this, and this is the efficiency and G by T sys. Just for completeness, I put it. Then coming to signal transport system, I think I'm lagging 5 minutes. Okay, the signal transport system, as I told you that the GMRT array is distributed over 14 kilometer radial distance, whereas the fiber distance is like, sorry, about 22 to 23 kilometer distance from this point to the faraway antenna. How do you bring the signals from these antennas? That is the novelty here. Right from day one, we started using optical fiber to bring the signal from the remote antenna to the central processing station where it is digital signal processing happen, and through optical fiber. And it is not that we use any digital Ethernet links or any other digital mode. We have used RF over fiber link. So we bring the RF directly what received by the feed all the way through the fiber and connect it here. Each antenna has 2 fibers in the legacy system, and in the new system there are some challenges. So when the upgrade started, people started asking whether you wanted to do an analog link or a digital link. Okay, so then we said that okay, I'll provide the facility for both. Either you can use analog or digital. Since we have technology with us analog, let us go ahead and do it. And digital, we can start doing it later. So one fiber was allocated for analog communication, and other fiber we allocated for digital communication. So the earlier bidirectional, I mean on two fiber communication has made into a single fiber communication in the upgrade. Okay, then they started, do we have to shut down the telescope during the upgrade? No. What we have done is that in the single fiber, we are assigned 4 wavelengths. We started supporting the old IF based system, the legacy system, in one of the wavelength, and the upgraded system, the direct RF without any down conversion from the system directly goes through 2 different wavelengths. So we get 3 wavelengths passed on to this 1550 nanometer wavelength and reaches here, and we split it and we give it to the respective systems on the central electronics building. And same way, the reference signals for the old system is done with a bidirectional link. A 1310 nanometer signal flows on the same fiber in the reverse direction and connects to the antenna for communication and monitoring purpose. That is how it has been done. So we can upgrade it in parallel. Yes, since it is all individual, you can start upgrading the system without disturbing any observational requirement with the older system. Then we thought of having a noise cancellation with RFI related. Yes, we have a 4th wavelength. You can use this for monitoring remote RFI, radio frequency interference, and start planning for noise cancellation techniques. The second fiber, yes, they provide for the direct digitization, and as well as Ethernet over. Here we have an analog old FSK modulated link in the legacy system, but now currently we have 1 Gbps line to every antenna to communicate as well as to monitor. And now what happens is, like, people wanted to retain the old system as well as the new system. So everything goes parallelly in the upgraded GMRT. Now, this is the legacy system. You have the front end antenna, front end, and the antenna based receiver, which actually down convert it into lower frequency, and then the fiber optic system transmit it and takes to the central electronics building where signal processing is done. But in the upgrade system, we have removed this entire block here. The signal all the way received by the front end, that is directly modulated onto the laser, and it is brought to the receiver. And here, most of the signal processing further, the analog and the digital is done in the receiver building. So the complication at the remote station is reduced, as well as the broadband performance is also attained here. So this is the upgraded system. So what is RF over fiber? You have a laser diode, and in the receiver room, you have a photodiode, a connecting optical fiber, and the LNA. This is the front end electronics. Okay, and here the antenna, and you take the RF output. So it's so simple on that. But when you give a signal here, you are converting an electrical signal to optical. So there is a conversion loss. Okay, again, you are converting back from optical to electrical. There is one more efficiency factor here. So overall, you will have about 36 dB conversion loss, 30 to 36 dB conversion loss happens at both transmitter and receiver. So we have to support that loss in the link. And since the LNE is in the front stage, we are not losing any noise performance using the RF over fiber technique. That is how we are able to use for GMRT. So this is a system. We were trying to take it to international community for little, what do you call, we have this facility and it can be used at this cost per antenna kind of thing. So this is totally in-house built, and it has a range of like greater than 40 kilometer distance. We have 3 gigahertz bandwidth and high dynamic range and single mode fiber. And this is the entire system in a antenna. Okay, we have tested the same link over 61 kilometers. You can see the noise floor and the actual signal after 61 kilometers with an input of minus 20 dBm. So we get sufficient signal to noise ratio even after 61 kilometers. Now we are working on 100 kilometer based systems. So what are the challenges here? You need to have very good amplitude stability, phase stability, high dynamic range, low noise figure, then optically induced noises, better reliability, and optical budget. So we'll quickly go through it. The optical transmitter has these modules. I have to introduce you to tell further. You have a laser and you have a monitor photodiode built inside the laser module, and you have a thermistor to monitor the laser temperature, and you have a Peltier cooler to cool the laser. Okay, so this is a laser module. What is the circuitry we have? We have an automatic power control circuit which takes the input from the monitor photodiode and sees that whether there is any variation in the optical power output. So this is an APC control. This is a thermoelectric controller. It measures the temperature of the laser and heats or cools the laser based on this Peltier, using the Peltier by this circuit. And we have a slow start power supply because any sudden transients will damage the laser, which is around like $1,000 each. Okay, now coming to laser APC control. In a laser, this is the characteristic. So you can see that the threshold and the laser power increases as you increase the current to the laser. But as the temperature varies, the curve gets shifted. And if you are biasing the laser at this point, okay, when the curve shifts, it is like here. So the power will be around 5 dBm, whereas here it is around 8 dBm or 8 milliwatt. Okay, and when it goes to higher, the same 60 milliampere current will be like 2 milliwatt power. So this power variation should be tackled. And other thing is that, you know, any Fabry-Perot laser or the distributed feedback laser, they're all some grating based and distance between the mirror and the laser. Their length variation could shift the wavelength emitted wavelength. So that is also critical. So we have to ensure there is no wavelength shift as well as the power variation is controlled. So we started using this APC control facility. I told you that. So with that, here you can see the temperature is varying like this. Okay. And we try to vary the bias to the laser with the APC control accordingly. If the temperature goes down, we increase the laser power, increase or decrease the laser power. Like that, we change the opposite trend so that you maintain the laser constant. Okay, the laser output power constant with time and with temperature variations. You vary the bias control and you maintain it constant. Okay, this also ensures there is no wavelength drift or shifting by the laser. Then there is a phase probability, stability problem. You have a bare optical fiber, it shows a thermal variation and the phase keeps changing. So what you have to do is you have to bury the fiber optic cable, and even in the legacy system, the cables are buried, and at 1.5 meter depth, you can see the variation is less than 0.5 degrees for 24 hours. So when we started using a 23 kilometer phase stability measurement, okay, in 24 hours, we can see that a slow phase variation happening because the temperature fluctuations are very small and we don't have a large phase change happening. So by this, we are able to meet the phase stability requirement. In addition, even the small phase change does not affect. The reason is that the astronomers try to calibrate the system every now and then, say every 5 minutes or less than that. So this slow variation is easily one can calibrate it and should not be a problem. And this is the various things which create the phase change. The main thing which changes with the temperature is the refractive index of the fiber. It changes a lot with the temperature, and that contributes more on the phase change in the fiber. The second problem is the optical intensity. So normally the connectors are like flat polished. When the laser is giving light in the fiber output like this, at the connector, some of the light get reflected back and enter to the laser and start giving these kind of periodic things in the RF spectrum. This is due to the Fresnel reflection happening in the connector side. So to avoid it, we started using angle polished connectors. So when the reflected light comes at 8-degree angle, they don't enter straight, but they get deviated, deflected and goes out. But the problem is we were using an APC type connector where this has a lock and key ferrule. With wear and tear, this 8-degree plane with the second connector doesn't match in line. Sometimes they get twisted. That started giving much more periodic things happening. So we started finding out the connector, very first we started using a push and pull type and an angle polish connector where this threading is not there, and this is called E2000. You can have 2000 times in and out this connector, and the connector gives a reliable performance and reliable reflection level, and they quote around like minus 80 dBm is the kind of optical reflection you see from this. Then there is another problem called Rayleigh backscattering. In the fiber, there is a backscattering happens, and this backscattering thing will give along with your signal unwanted spikes randomly appearing in the spectrum. So this reduces the signal to noise ratio. So what we have done is we have used an optical isolator, what you see here, a small one, which is around 45,000 in rupees. And this one has a feature like this. Suppose a signal is coming with a polarization 0 degree like this Faraday crystal rotated by 45 degrees. When the light is getting reflected back, it rotates further to another 45 degrees and it goes like this. When you do that, this polarizer, it will be orthogonal. The reflected light will be orthogonal to this initial polarizer, and no light goes out of this back to the laser. So this kind of performance is done by this isolator, and after implementing it, you see this noise floor very silent with no random noise fluctuation seen here. Then the optical budget, yes, we have used a high power laser, and we had an additional 10 dB margin where we can go to 33 kilometer distance further. Then we have a better gain return loss for the fiber optic system. We have signal to noise ratio, performance with loss and gain performance we have studied well. And we have inserted the amplifiers before the transmitter and receiver to compensate the conversion loss as well as to reduce the noise figure of the fiber optic system. And this is an important thing. What we have done is that we have given this curve. Input power versus output power is a linearity performance of any RF system. And we have measured it for different optical power. And we have found that an optical power of like minus 5 dBm has a larger, larger linear performance, even 0 dB we have. But we can't go for high power because the system gets limited with laser noise. And these regions like minus 5, etc., it is a thermal noise limited system. And we started operating all antennas uniformly at minus 5 dBm and with a 10 dB margin here. And phase noise also we have studied for the system. Suppose you wanted to carry a calibrating signal or some reference signal, you can do it. We have a better phase noise performance of this system. And this is the remote signal what we have got it. This is an L-band system. You can see so many antenna signal coming to the receiver building through the RF over fiber link. These are our friendly mobile signals coming into the band. Okay, this is the GEO and this is the GSM signal coming into the band. You can see how all these bands are faithfully brought to the central electronics building by the RF over fiber link. Now, let me quickly go through this future scope. In future, we wanted to replace the horn antenna for the L-band. We started building this kind of cross dipole compact, and we wanted to put the LNA behind the dipole. It is almost through. We will do a final evaluation and finalize this. Then the next one, we wanted to build a narrowband LNA because our LNAs currently are very wide, and we have made it very wide, more than the required bandwidth. So this started inviting a lot unwanted signals, like the mobile signals at 1800 megahertz and the GSM and CDM geo kind of signals. We wanted to make the LNA narrower so that you can bring only the signal and keep all the spectrum silent to the LNA. When you do that, the receiver doesn't get saturated much, and the LNA becomes highly linear for large interfering signal. So this is our upgrade plans. Sorry. And then we have, for the same interference purpose, there are signals falling outside the band for the systems. We started using a new design, metamaterial based direction coupler design. Suppose there are two mobile signals here, in the lower band, they try to beat each other and try to create a product falling into the desired band for the radio astronomy. So how do you remove it? You try to reduce the bandwidth seen by the LNA. So this direction coupler is behind before the LNA. Okay, so this has helped in improving the dynamic range of the LNA further and without degrading any system temperature. You can see this interfering intermodulation product disappeared with this design, and we are evaluating it, and quite soon we will move to this design also. And then we wanted to do a calibration by radiating from the antenna prime focus. You radiate to the feed and you try to characterize the entire system, receiver system, including its stability, gain, and performance, everything. So we were trying with some log periodic antenna mounted here, broadband antenna, and try to receive the signal and started doing experiment with that. So this apex radiation method of calibration is being planned. And this is another novel design. You know that Professor Vaigupta has mentioned we are working on phased array antennas. This is one of the antenna. This is a Vivaldi antenna built by Astron. So we are working on it. You can see 144 elements here. But how do you connect all 144 elements? We need a fiber optic system to bring the signal all the way for signal processing. So we have designed a small optical transmitters and receivers just weighing 116 grams each. And we have packed behind these elements. You can see 60 of them has been assembled behind the phased array antenna, and all signals are brought together over optical fiber, and a two big multi-core cable brings the signal all the way to the from the prime focus to the antenna, and for further signal processing could be done. So the fiber optic system is ready. The other antenna design and the back end people are working on. Once that is there, then this upgrade also will move on. And we wanted to have digital signal processing systems. I mean, digital signal transport system. Suppose you are digitizing right at the antenna base itself. Yes, we have a new system already tested. You can bring two 10G lines from remote antennas with a what do you call reference signal for the same digitizing purpose, and the telemetry signal for antenna control, all put together on the second fiber which I told you. And these systems work for 80-kilometer distance, and the system is ready for further upgrade to with the digital signal transport system. Then we have another work. It is called notch switch filter band. In case you want, the astronomers wanted to use additional filters to make that band clean, we are working on a cabinet kind of thing which has multiple filters integrated. You can switch them and combine some of things like wireless and a TV signal could be combined into a band. You can combine a satellite and a TV signal as well as a mobile signal together and use it. So all those combinations are available, which is switchable for every antenna, and it is located in the central electronics building for processing the signal based on the requirement. And the other thing is that we wanted to have RFI monitoring stations, like a minimum at least 7 stations, and bring the signal through the 4th wavelength and try to do this real-time RFI mitigation and as well as noise cancellation technique in future. Then this is another interesting project. We started building, you know, Faraday cage. We started building a big storage building inside a Faraday cage. This entire building is placed inside a stainless steel mesh. Okay, and it gives a very good isolation. You can't see a mobile signal or a satellite signal inside the building. Then we wanted to carry the signal to NCRA, which is about 100-kilometer distance. We are upgrading our link to 40G lines, like we wanted from GMRT via Rajgur Nagar and Narayangarh. We wanted to take it to NCRA campus with a 4 10G lines we are working on, and already 1 10G we established and tested over here. So this will give a dedicated traffic for data transport. And this is my references, and this is my team who have been working very closely with me, and innovative ideas just keeps popping out from them, and we work together. And So that's it. And thank you on behalf of my team.
Thank you, Suresh, for a very, very nice talk. Covered lots of aspects of the RF and fiber systems for the mainly for the upgrade, but also looking at many other systems that you described towards the last part of your talk. Highly challenging works, but also very convincing data and results. And obviously, the quality of the data actually says that all the systems have been performing flawlessly. So thank you, and also to your entire team on the screen for doing such a great job. So I think there are some questions. So I request anybody who is on Zoom, of course, they can unmute and start asking the question. Okay, let me see. There are a couple of questions already. This is Aditya. What is the advantage of RF or fiber or direct as compared to the direct digital conversion at the RF front end itself and transmitting digital signal over fiber?
Correct.
You had,
yes. I'll answer this. Actually, I don't want to get biased on this. Like digitizing at the antenna base and bringing it through digital line, that's quite good enough because you are freezing the amplitude and the phase there itself. And the phase and amplitude doesn't change after that. But in RF or fiber, the amplitude and phase stability over the long distance, you have to ensure they are good enough. That is one thing. But the other part of the digital system is that they produce radio frequency interference. When you try to locate at the antenna or at the prime focus, they started producing interference and shielding solutions. And I think there are no much solutions are available, but one has to work a lot to keep these interferences low. And the other point is that for the low frequency, the phase and amplitude variation is controllable and it could be handled very easily with a careful design, what I have told here. Like with the APC control, I could maintain a very good phase, amplitude stability. With a buried fiber, I can create the slow phase variation, which is easily, one can calibrate it at low frequency things. But certainly for high frequencies, for long distance transmissions could be a problem. But for GMRT, it's a perfect solution and it's a cost effective and no interference, and it is easy to implement also. And we have a solution with us. I think I answered your question.
Okay. Yes. There's also a question from V. Mahadevan. What is the expected performance of the new array antenna as compared to the existing parabolic dish?
We have not done an antenna. We are working on an antenna which is obtained from Astron. So the beamforming work is being done. But only thing I can say that the RF fiber system for this array antenna, the backplane, the fiber optic backplane, we are ready to it. So I can't say anything on the performance.
Okay. While I'm waiting for other questions to pop up, can you say a little bit more about your Faraday cage? Nice thing, which you just passed me, but you didn't tell a little more details about it.
Okay. So actually, the GMRT builds an auditorium and an exhibition hall, okay, and labs. The labs which wanted to use a lot of digital systems and computers inside. But it is like my director used to say, the earlier director, that you are asking permission to smoke in a petrol pump. It's like that. You wanted to do all these things, inviting so many outsiders and have lectures, auditorium, and exhibition, and a digital system with a lot of computers. You produce a lot of interference to the observatory. So you will lose everything. So the thing is that we started working on a Faraday cage. So from the plinth level, from the floor below, okay, and to the mesh grows, the stainless steel mesh grows all the way along with the pillar and then on the side walls, okay, both inside and outside, and the entire building is grown with the mesh, okay. And other thing is every labs are double shielded once again internally, and we have shielded doors through which you enter, and we have shielded windows into it. The more interesting point is that how do you shield your drainage and water pipelines? So our colleague has worked a lot on that by making a waveguide designs and mesh for it. And then how do you take the power line and the air conditioner into the building? So they are all done with waveguide designs. It is interesting design, and I think quite soon that will be open to the public, maybe next year. So we have seen about 30 to 35 dB isolation in the building, and some more interior work is happening, and after that it will be released for public. So it's an entire Faraday cage, and it gives this kind of isolation. So we are safe operating things, and but certainly no mobile inside the Faraday cage, because you don't get any signal. Even GPS signal you don't get inside it. So that is the quality of isolation.
Interesting. So when you say the 37 dB isolation and so on,
yeah.
So are you also, try to install, let us say, test sources which are kind of close to the frequencies of your interest?
Yes,
or
yes.
huh?
We have spherical dipole antennas as well as log period antenna. We actually place them inside, radiate it, and we measure outside. And same way we radiate outside and we measure inside. So we try to do in all sides as well as on the terrace to that level. Okay, and at a distance of 3 meters, 10 meters, and larger. So we see at these distances also, so that your measuring system is not saturated. So we take care these things, and the value what we get is around 35 dB.
Very interesting. Yeah, yeah, great, nice work. And there's one question possibly you have actually dealt with, but maybe a couple of words you can say about it.
Yes, sir.
This is Vidya Naik. Great job, Suresh. Congratulations to your team. What is the key design factor in achieving low noise temperature?
Okay. Achieving low noise temperature. Okay, it is the same standard things. Like you have to see the device. What you have, we have used a PHEMT device. Okay. So they are actually low noise transistors which has been used in this. The thing is that you have to understand the device much in designing your input out matching circuits, and the biasing is more important. Your biasing should be of low noise enough so that you try to get the low noise performance of your system. So it is like multiple parameters in the LNA design, not only the low noise, you have to optimize the stability of the LNA as well as the dynamic range of the LNA is important. And in addition, the bandwidth, we couldn't control it. So most of the LNAs you see in other places, they are wide band because people leave it like that. Okay, let it go all the way it is possible. But for a radio astronomy, we understood that by keeping it wider, you invite all unwanted things out of your band coming into your band. So we started working on narrow band LNAs also by integrating some filters in the design. So this is how it works. And it's the final level is the device limitation. You can't go beyond that.
Yes. Okay.
I don't know, I've answered it.
Yes. Are there any questions to Suresh? Suresh, I want to ask a question which is slightly outside your scope of the talk. Yes, I'm sure there must be a lot of interactions and spin-offs of your work and your team's work, and of course, in general, the GMRT, yes, which are obviously all this work has a potentially large applications and collaborative programs with outside industry and maybe similar other institutions.
Yeah, actually, we didn't have the luxury of collaboration outside, but very good results are there from antenna designs on the RF electronics and EMI EMC, that is a RFI mitigation. So our group and the fiber optics, our group have a lot of results on that. And to be frank, there are not much publications has been done because we were busy. Now we have to slowly start that also. So that is there. Yes, we have a lot of things to talk and present also.
No, I was not, okay. I mean, my question was not so much on the publication part, but I was saying that whether there were some tie-ups or, spin-offs into industry, let us say somebody came and kind of looked at the possibility of using some of the technologies that you developed
Yes, sir. I understood. Like we were trying to push through SKA, but we were a little bit late on the fiber optic system. EMI, EMC also we are a little late to enter into it. And there are things with some requirements from ISRO, some discussions we had, and then with RRI. Other than that, we don't see much of industrial. But we have developed the industries by producing radio frequency interference computers, UPS systems, switches, all those things, where the industry has taken our results and started getting through on their low EMI products, because we test them free of cost. We give solutions to them for our requirement, and that has gone to the industries in developing things. So not much with the industries has happened. I don't know. Still, I am up to the point what you asked.
And I was just asking because this is potentially, the work which is obviously of very high value, which probably can also have a good potential spin-offs into in academia, industry collaborations, and maybe patents, maybe other such activities. So I was kind of trying to probe.
Right. We lag on that, to be frank, because we are remotely located, you know that, and our only friend is Google. Okay, and so it's quite a less interaction with the outside world that is there. Maybe things can improve.
Okay, so are there any more questions to Sureshkumar? If not, once again, let us thank Suresh for his wonderful talk, and also congratulate him and his team and the entire team, of course, at NCRA and GMRT to continue to work at such a front-ranking technologies and doing a great work. And all the best for your, of course, upgraded GMRT, but also many endeavors beyond that, including your SKA and other aspects. So thank you very much, Suresh.
Thank you, sir. Thanks for the opportunity. Thanks on behalf of my team also.
Bye-bye.
Thank you, sir. Bye.